Hello everyone, welcome again to this third part of the series. In this part of the video, we will be creating the machine learning model. If you haven't watched the first two parts, I would strongly suggest you to go and have a look at it, especially the second part of the video, the second part of the series. In the second part, we did some EDA and we did some feature engineering, and I can't stress that enough how much paramount it is that you go and have a look at it. Because by now, our entire dataset is almost ready to be fed into the machine learning model. Just to recap, I told you that machines understand only and only numbers, so it is our job as a data scientist or a machine learning engineer to convert all the features into such a format that machines can understand. So it is our job to convert all the values, all the features into a numeric format. So to convert them, we use encoding. Today, in this third part of the video, we will be creating the machine learning model, to which we will be requiring to do one last step to pre-process the data, that is normalization. Now, normalization or scaling is used to bring down all the features to a common scale without distorting the differences in the range of the values. For that, we would be using the standard scaler, and then we would split the dataset into some, let's say, 90-10%, where the major part, the 90%, would be reserved for the training purposes. Then we would build a machine learning model. We would try to create at least one or two machine learning model, or at least we would try, as long as we don't reach a sufficiently high accuracy, and then we would want to evaluate our machine learning models on unseen test data. We don't want to do the evaluation on the training purposes or the training data, because it would backfire. It would not make much sense. We would want to see how well our machine learning model can generalize on brand new unseen test data. So let's start our journey. So this is our dataset. So far as you can see, we converted all the columns, all the features into numeric format. But there is a problem that you can see. For example, first problem is that price is in 4-digit, the values are in 4-digit, while let's say arrival time in hours is only in single or maybe 2 digits. Now this would give a false sense to the machine learning model that perhaps price, alright, so price is the target variable. Alright, let's take another example, okay? Let's take duration over here. So duration is in 3 digits, right? And sometimes in 4 digits, while arrival time in hours is in single digit or perhaps sometimes in 2 digits. Now, if we were to do nothing and were to feed this into the machine learning model, it would give a false sense to the machine learning model that perhaps duration is more influential in predicting the price, or vice versa. Now, to bring all the features into common ground without distorting the relative differences, we would want to normalize. For normalization purposes, we would use standard scaler, but one thing, just for our convenience, what we have to see is that we want to predict the price. So let's push this price column towards the end of this data set. So I would want to do that. So for that, I will write a piece of code. Let's do that. I'm going to create a temporary column is equal to data.columns.toList. Right, I'm converting all the columns to a list, and for the visualization purpose, I will print this now. \n, and then I would want to create a new column, right? And I would want to say the thing is, I want to create a new column where, except this column with index 2, like 0, 1, 2, I would want to have everything. So I will take these first two rows with index 0 and 1 plus, these two columns plus the columns with index 3 onwards till the end, right? I would not touch index column 2, And towards the end, once I've created this new column, I will add the second column that index, sorry, the third column with index 2 towards the end. That's the idea over here. So I'm going to say new column is equal to temporary columns. Fetch me the, all the features from 0, from the beginning till the index 2 plus temporary columns from 3 onwards till the end, right? And then once you've done that, take the new column, like take this column at index 3 and append it towards the end. So I would say new column dot append, append temporary column with index 2, something like this. Now for visualization, I will print it simply. I would say print new column, right, and \n, and I would want to now re-index the entire I would want to re-index the columns now. So I would say data is equal to data dot reindex columns is equal to new column, right? And let's say data dot head to print the first 5 rows of this data frame. So if should I execute this, I will get something. Oh, data is not defined. Oh, excuse me, I need to run up till here. So I would say restart and run all. Yeah, give them time. Right, so over here, right, perfect. So excuse me, we could see that initially the price was in, over here, but then after our rearranging prices towards the end, and have a look at our data set, our price column has gone towards the end. Now we would want to normalize the data set, right? For normalization, I would be using the standard scaler. So I would say from scikit-learn dot pre-processing import standard scaler, right? And then I would create an object of this library. I would say scaler is equal to standard scaler, right? And I would want to fit the fit this into the machine into our data sets. I would say data is equal to scaler dot fit transform fit underscore transform data. And to see how it works, I will only fetch the first element of this. It will create a kind of a matrix. So I would fetch the first element over here, and it would give me something like this. All right, perfect. So there should be 34 columns. So there are, as you can, if you were to count 1, 2, 3, 4, 5 rows total. 1, 2, 3, 4, 5, 6 of them. So 6, 5, 30 plus 4 of them. So there are total 34 values representing 34 columns. So it's working fine now. Now I would want to split the entire data set. So I would say from scikit-learn dot model selection import train test split as, I don't want to type this entire thing again and again, so I would say TTS, standing for train test split. And I would say that my feature variables, all of them, like all these features, starting from duration up till let's say route 5, are the feature variables, and my target variable is price. So I would say fetch me all the rows over here. I would say x is equal to, or the feature is equal to, data fetch me all the rows, comma, fetch me all the columns up till the last one. Do not include the last one. So something like this. And y, that is the price one, I'm going to say data fetch me all the rows and fetch me the last column, right? And something like this excuse me, something like this would happen. So let's execute this. We have successfully executed it. Now let's try to split it properly, right? So we would want to say x train, comma, x test, comma, y train, comma, y test is equal to train test split, right? Plug in the values or features, that is x, comma, y, comma, make sure how much test size you want. So I'm still gonna say I will need the test size to be only 10%, so 0.1, and my the seed value is going to be random state, is going to be some random value, so that if you want to recreate the same result, we can do that by mentioning the seed value. That is going to be, let's take some value, random value 69, something like this, and let's print the shapes, right? So let's say x train dot shape, print me the x test dot shape, print me the y train dot shape, and finally print me y test dot shape. So let's execute it. Right, it's working perfectly fine. Now we would want to create first model. Since it is a we have to predict the price, it's clearly an example of a regression model. So let's do that. We'll say let's create a linear regression model, right? So I will say from scikit-learn dot linear model import linear regression, right? I'm going to create a an object of this. So I will say model. Okay, let's give it a break. The model is equal to linear regression, something like this, right? And then I'm going to create the machine learning model using the fit method, and I will pass in the parameter. I will pass in the training data and the x training and the y train. So it's say x train, comma, y train, something like this. And hopefully it would have created it. So let's do that. Let's execute it. Right, it has created. Perfect. So before we move on, let's try to evaluate this thing, right? So for that, we would require some metrics. So I would say from scikit-learn dot metrics. Now there are several metrics like root, mean, square, error, coefficient of determination, or what we call R2 score, or maybe absolute mean square error, different ones. So I will take only two of them. That is the mean squared error, the root mean squared error, RMSE, and the R2 score, the coefficient of determination. So I would say from scikit-learn.metrics import me the mean squared errors, right? I will take a root of it, and then also import me the R2 score, something like this, right? And now I'm going to create a method to define the metrics, right? So that it will take two values. First, it will take the true value of the true value. I would say y true, and then it will take the predicted value, right? And then it will give me, it will print all of them as such. So to find the how value model is doing, you would require the true value, the observed value, and the predicted value that your machine learning model would have predicted. So I would say print me the RMSE being, I would say take the square root of, so I would say mean squared error. Oh wait, it has to be error, not errors. So I will remove this s, mean squared error, right? Plug in the values being y true and y predicted one, and take the square root. So let's say square root being 0.5, raised to the power 0.5, and also print the r squared value. So I would say r squared value being R2 score, plug in the values of y true and y predicted one, right? And let's see if it's are we missing anything? No, I don't think so. right? And then I will create another method to give me the accuracy. These are the metrics, right, which would help us to find how well our machine learning model is doing. Let's find out the accuracy. For that, we will be dealing with the we will have to find the mean arithmetic percentage error. So I would say define accuracy again. Method, it will take the same parameters, so y true value and the y predicted value, and it will find the error. So it will say errors is equal to the absolute value of the difference between the predicted and the true value. So I would say y, let's say true minus, let's say, y predicted value. Regardless, either way you can draw, because anyway we're taking the absolute value only. Then I would say the mean arithmetic percentage error is equal to 100 multiplied by the mean of numpy dot mean of the errors divided by the y true as such, and the accuracy will be given by 100 minus this mean arithmetic percentage error, and at the end you have to return me the accuracy, right? Am I missing anything? I guess no. So I've executed. Let's try to find the let's first find the predicted value, the values that a machine learning would have predicted on the X test. So I would say y predicted value is equal to model, our object of linear regression, model.predict method, and plug in the value of X test, right? And let's plug in this value as well into the method that we've created. So I would say y test, right, and y predicted that we had just calculated, and it's going to give me, right, perfect. So it's giving me the RMSE value to be about 53.6% and the R squared value to be at 64.5%, and the accuracy is going to be, plug in the same value, I would say y test and y predicted, and it's going to give me, let's say, about 70.38%. Perfect. Well, our accuracy on unseen brand new test data is about 70.38%. So let's try to find out if we can do any better. Well, we know that there are certain machine learning algorithms which would definitely do better than this, and one such algorithm is the pick an algorithm from an ensemble technique algorithm. So let's talk about let's use random forest for a change, shall we? So let's use the random forest, and let's see how well it would work on random forest. For that, we will have to import it. So I would say from scikit-learn dot ensemble, import me the random forest regressor, right? And here we would want to create an instance of the random forest model, and just to distinguish it bit from the linear one, I will give it another name instead of giving just model. So I would say model underscore random forest, right, is equal to random forest regressor, and I want the number of estimates to be about, let's say, some value about 500, and minimum sample split be equal to, let's say, 3, right? And then I will create the machine learning model using the fit methods. I would say model underscore random forest dot fit, plug in the values of X train and Y train, right? And let's see, oh, there is a problem. Oh, it has to be number of estimators, not estimates, right? Still again a problem. Minimum sample split, what am I doing? Okay, it has to be minimum sample split. Okay, perfect. Let's execute again. Let's take some time. Right, that's expected because again, it is random for it's an ensemble technique, so it's kind of a huge algorithm. Let's see how long it takes. Right, perfect. It has built the machine learning model. Now let's try to predict using random forest on the X test. So I would say predict underscore RF for random forest is equal to model underscore random forest. Plug in, dot predict, plug in the X test, right? And it should work, perfect. And now let's look at the metrics. So I would say metrics, plug in the values, Y test, right? Unseen dataset, true unseen dataset, and this here would be a predicted unseen, predicted values on the unseen dataset. So I would say predicted RF. It's going to, it's giving me RMSE value to be around 39.3% and R squared value about 80.9, around 81%. Okay, so let's find the accuracy as well. So same thing, Y test and predict value using the random forest. Hopefully it should give me some better value because it is giving me a very high R squared value compared to the linear regression one. So it's going to give me, let's see, oh, perfect. It is giving me 99.723%. This is an exceptionally high accuracy for our machine learning model. So over here, throughout this series, we started a journey with, the price, flight ticket price predictor dataset. In the second video, we did a lot of EDN feature engineering, and in this third video, we created the machine learning model. And first, we normalized it using standard scalar, and then split it, and then we built two machine learning models. Turns out, according to our common knowledge, it has outperformed linear regression, where there are multiple features, to predict a regressive value, and using random forest is giving me over 99% of accuracy on an unseen dataset. This wraps up our entire series, and if you've liked so far, I would urge you to subscribe to this channel and share this with your friends who might be prepping for a data science or machine learning interview, or who may want to get some help. Till next time, cheers.
Project Pro, the only solution for solved industrial grade projects.